Welcome to this explainer. Today, we're taking a look at a truly brilliant piece of engineering, the continuously variable transmission, or CVT. For decades, automotive engineers faced this massive bottleneck when trying to transfer power from an engine to the wheels. So today, we're going to look at the CVT not just as some car part, but as an elegant, mathematical solution to a fundamental mechanical optimization problem. Okay, let's dive into the blueprint for our mechanical teardown today. First up, the gear optimization problem, then variators and effective diameter. Third, mastering the slip constraint. Fourth, precision hydraulic actuation. And finally, efficiency, sound, and droning. So, part 1, the gear optimization problem. To really get why the CVT is such a game changer, we kind of have to look at the historical flaw in traditional transmissions. Imagine climbing an infinite staircase. In a standard gearbox, traditional gears are like these discrete stepping platforms. You accelerate, the engine RPMs rise, and then, well, to keep going faster, you have to shift. The RPMs drop back down, and you start the climb all over again on the next platform. It's literally a series of steps. But a continuously variable transmission, it's completely different. It's not a staircase at all. It's an infinite sloping ramp. This design allows for constant, uninterrupted upward acceleration. Because there are no discrete gears to shift through, the engine never actually has to drop its RPMs to move to the next level. And the real-world impact of that ramp versus the staircase is absolutely massive. With a manual or a traditional automatic, those fixed transmission ratios literally force your engine out of its optimum power band. You get this jagged sawtooth pattern on an efficiency graph, right? You rise to a peak, shift, and fall back down, which completely interrupts power delivery and causes what engineers call shift shock. A CVT, though, continuously adapts. The RPM behavior stays constant right at its absolute peak, tracking perfectly along that optimal efficiency line. The power delivery is totally uninterrupted and seamless, so you get maximum fuel economy and maximum power exactly when you need it. Moving right along to Section 2, variators and effective diameter. So how do we actually replace all those clunky interlocking steel gears with this infinite ramp? Enter the variator. This is the heart of the whole system. It's a core assembly made up of 2 adjustable conical pulleys and a high-tension connecting belt that seamlessly changes the gear ratios. Instead of having fixed gears of different sizes, the variator basically acts as a dynamically sizing gear. And the crucial thing to note here is that on each of these pulleys, one side of the cone is fixed firmly in place while the opposite side is movable. Now, what's really interesting here is the core logic of how these components interact. The primary driver pulley on one side and the secondary driven pulley on the other move in this synchronized seesaw action. When the movable side of one pulley squeezes inward, it gets narrower, which forces the belt to ride higher up the cone. But at the exact same time, the other pulley widens out, letting the belt drop lower into its groove. It's just a beautiful, continuous, fluid exchange. And that brings us to the concept of effective diameter. This is the dynamically changing diameter of the pulley's contact point with the belt. As the belt rides higher or lower on those cones, the effective diameter changes instantly, and that's exactly what determines your output speed ratio. Here's where the engineering gets incredibly precise. Both the belt and the inner walls of the pulleys share an exact 22-degree cone angle. Because they match perfectly, the belt has full, flush contact no matter where it sits on the radius. And that is what allows the system to create an infinite number of ratios, perfectly mapping the engine's output to the wheel speed. All right, Section 3, mastering the slip constraint. Now we've got to introduce the main engineering antagonist in this mechanical optimization problem. Think about it. If the CVT is mathematically ideal and perfectly maps to an engine's optimal efficiency line, why did it take so long to become standard in modern cars? Like, why were early CVTs only found in small scooters or low-torque applications? It really makes you wonder about the inherent physical limitations that held this whole technology back from heavy-duty driving for so long. Well, the answer is the slip constraint. See, unlike traditional transmissions that rely on the unbreakable physical barrier of interlocking steel gear teeth, CVTs rely entirely on friction, and friction is absolutely everything here. If the belt slips against those smooth conical pulleys under heavy acceleration, you immediately lose power, you generate catastrophic heat, and the transmission essentially destroys itself. So maintaining exact immense tension is quite literally a matter of survival for a CVT. To combat this, engineers had to completely rethink the belt itself. Here is a massive misconception. This is not some rubber belt that just pulls like an alternator belt. No way. This is a highly complex, high-tension steel link belt. It's made of flexible steel ring packs that hold together hundreds of precision-machined steel elements. And here is the true genius of it. It pushes the driven pulley rather than pulling it. As torque is applied, all those tiny steel wedges compress against each other, transferring massive rotational force through compression, all while maintaining that vital friction on those 22-degree cone walls. Which leads us perfectly into Section 4, Precision Hydraulic Actuation. Okay, so we know we need extreme friction to stop the slip. But what actually supplies the muscle? The solution is hydraulic actuation. This is the use of highly pressurized transmission fluid, which is precisely controlled by microprocessors, to literally force the movable pulley halves together. It dynamically manages the clamping force to keep that steel link belt locked exactly at the required effective diameter. Without this extreme fluid control, the whole system just falls apart. And this control loop happens in a fraction of a second. Boom, a heavy-duty gear pump driven by the engine generates intense fluid pressure. Almost instantly, a directional control valve, which is constantly listening to commands from the car's computer, routes that pressurized fluid. Then, hydraulic actuators, which are essentially giant pistons housed right inside the pulleys, clamp the movable pulley sheaves together. This entire system has to respond to throttle position, vehicle speed, and engine load in real time. It's constantly adjusting the fluid balance between the primary and secondary pulleys to change the gear ratio while maintaining an absolute death grip on the belt. And this brilliantly illustrates just how staggering the engineering required to make this work really is. You've got a complex hydraulic drive system featuring a high-pressure pump, directional control valves, choke valves, and various feedback sensors, all working in perfect harmony. The sheer complexity of this hydraulic circuit is exactly what prevents those belt slip losses and maximizes your vehicle's fuel economy. It's this incredibly delicate, high-pressure dance happening directly beneath your floorboards. Finally, Section 5, Efficiency, Sound, and Droning. Let's bring all this math and engineering back to the actual human experience of driving one of these mechanically optimized machines. When everything works as designed, the mechanical payoffs extracted from this elegant, continuous design are just massive. You get infinite gear ratios, meaning the car is literally always in the perfect gear. You get absolutely no shift shock or torque interruption. You get incredibly steady cruising speeds, the maximum possible fuel efficiency, and, funnily enough, compared to modern 10-speed automatics with all their multiple planetary gear sets, you actually have fewer overall moving parts. But there is a catch, and it has everything to do with how we as humans perceive speed. You know, drivers often complain about an elastic feel and this loud droning sound when they floor the gas pedal in a CVT car. Because the transmission is doing all the work of changing speeds while the engine RPM stays completely flat, the car just sounds different. But we really need to reframe this. That drone you hear? That is literally the sound of perfect, unbroken mathematical efficiency. It is the sound of the engine sitting flawlessly at its peak power band, while the infinite ramp of the variator catches up to the wheels. Which brings us to the ultimate psychological twist of this entire technology. Because we humans are so deeply conditioned to expect the sawtooth feel of a traditional gearbox, you know, the rise, the pause, the drop, the rise again, a lot of drivers absolutely hated the smooth drone of a CVT. So what did automakers do? Engineers literally programmed fake shifts into the transmission computer. They intentionally forced the hydraulic actuators to step the pulleys in discrete chunks. They literally program inefficiencies back into the system, dropping the RPMs purely to give human drivers the illusion of an old-school geared transmission. It really leaves us with a fascinating paradox to consider. As we finally succeed in engineering the mechanically perfect transmission, solving the gear optimization problem, and mastering the slip constraint, do we ultimately have to program its original flaws back in just to make human beings comfortable? It's a wild clash between pure mechanical optimization and human perception. Thanks for joining me for this explainer, and I hope this leaves you eager to decode the hidden engineering in the world around you.